Okay, so now that we understand that covalent molecules can be built from atoms using Lewis dot structures, and we can talk about molecular shape, today we're going to be talking about what aspects of the structure, so functional groups, make the molecule have interesting properties. Okay, so many of the really interesting molecules on this planet that are made out of covalent bonds are made out of carbon. Carbon is a really important element. We are composed of carbon. A lot of the products and things that we interact with on a day-to-day basis are also made out of carbon. And so if we're going to talk about what parts of carbon-based molecules are interesting, we should probably start our conversation with pure carbon, so just carbon structures. And there are a few of these. And that gives us to a definition, and those are allotropes or allotropes. So allotropes are the different forms of a naturally occurring element. And there are a handful for carbon, and they basically they all consist of pure carbon atoms, and they're bound entirely to other carbon atoms. So you can see, for instance, that this carbon right here is 4 bonds as well. And hopefully you can see, because these are 4 different things around them, and we're talking about molecular shapes, that every single carbon atom is tetrahedrally bound to every other carbon atom. And when that happens, you get a diamond. And a diamond is a macroscopic representation of this chemical structure, and a diamond is one of the hardest natural substances known, and their hardness is derived from this three-dimensional network of all carbon covalent bonds. You of course can come up with other ways to bond together all carbon, and one of those would be graphite. And so graphite is where carbon has 3 other carbons around it, and so the way that you got your octet there is you created a double bond. And so we know that when you have 3 other atoms around it, you are no longer tetrahedral, you're trigonal planar. And so because these are all trigonal planar, graphite is actually a series of 2-dimensional sheets. And they're only weakly held to each other. And so when you rub your pencil across a page, what are you actually doing? You actually are peeling off sheets of pure carbon, these pure graphite, because they're very strong in the sheet, but between the sheets they're actually quite weak, and they actually slide very easily. People have recently gotten very excited about not graphite necessarily, but graphene. So graphene is isolating a single sheet of graphite, and you can kind of see this is an image of a single sheet of graphite, and it kind of looks like a crumpled piece of paper. And this is a good image of it. You can kind of see it's a trigonal planar, 2-dimensional kind of structure. It kind of waves around. And people are now finding this is a pretty amazing substance. This substance is one of the best conductors known, and it's really good at conducting both electricity and thermal energy. And in fact, the Nobel Prize was won recently for the isolation of graphene and for its studying of its properties. And amazingly, the way that the people who won the prize discovered how to isolate a single sheet of graphene was using Scotch tape. They actually literally took a piece of Scotch tape and they put it onto the surface of a piece of graphite, and they actually peeled away layer by layer by layer by layer by layer until they had a single sheet left. And that is in fact the Nobel Prize winning discovery. And then they studied the single sheet, and they found that it had some pretty remarkable properties, which now a lot of scientists are very excited about turning into applications such as next generation microchips. Another interesting allotrope of carbon is actually the buckyball. And so this is basically a ball of carbon, and you can see that it's still composed of single and double alternating bonds, but instead of a sheet of graphite, it's basically kind of rolled up now into a ball. And these were originally discovered when lasers would hit carbon, and they would discover the formation of these kind of buckyballs. They have, as you can see here, similar to shape to soccer balls with alternating 6- and 5-membered rings. But now they've actually been found in interstellar space and in other places. So these are also a naturally occurring form of carbon. Okay, so now we've talked about just pure carbon forms. Let's talk about functional groups. And so the idea of a functional group is functional groups are common groups of atoms that occur in covalently bound molecules, especially off of carbon, that have predictable function or predictable reactivity profiles. So if you have an alcohol group, for instance, right? You see this R. There is no element R. R just means it's attached to the molecule at that point. So if you have an alcohol, for instance, like something like methanol, it's going to have some of the properties of the alcohol group. Similarly, ethers, ethers might be something like diethyl ether. So diethyl ether, CH3CH2O, CH2, CH3, sorry, kind of lost space there. So this is an anesthetic, and so a lot of ethers interact with our brain chemistry. And so having these kind of predictable arrangements of atoms provide us with a very quick approximation from perhaps what the molecule might do. So I'm going to take you through a couple of examples of functional groups and things that they do. Probably one that we're all familiar with is ethanol. Ethanol is right here. CH3CH2OH, it's an alcohol. And when you consume alcohol, your body recognizes it as a toxin. And so it attempts to detoxify your body of alcohol. And it does this through an enzyme. Enzymes are, we're going to talk about them in a little bit, but they're basically, they run chemical reactions in your body. And the enzyme here is liver alcohol dehydrogenase. It's an enzyme that's in your liver, and it actually causes the ethanol to undergo a series of oxidation reactions. And so it intentionally adds oxygen and converts the ethanol actually into a byproduct called acetic acid. Acetic acid is the same stuff that's in vinegar, and in this case your body can dispose of acetic acid quite easily. So here you have maybe some alcoholic beverage, and then as it is absorbed in your bloodstream and has to go through your liver transforms it into a waste product that you can get rid of, or actually even utilize sometimes. So methanol is also an alcohol. It's very similar to ethanol. It's missing a carbon and two hydrogens. So this is a very similar molecule, and it's also known as moonshine. It's also known as white lightning, mountain dew, hoochie hoochie mapuchi demba. There's all sorts of names for it, but whatever you name it, it's the same. It's pretty dangerous to drink. And the interesting thing is that methanol is quite harmless by itself. However, your body is tricked, and your body is tricked into thinking that it's like ethanol, its cousin, and it tries to detoxify it. And in the process, this liver alcohol dehydrogenase actually converts it into two quite dangerous molecules. One is formaldehyde and one is formic acid, both of which are quite toxic, especially formic acid. Formic acid, among other things, damages the optic nerve, so a common side effect of methanol toxicity is people go blind because it just destroys the proteins in your eye. And actually, respiratory failure and death are pretty common as well with methanol poisoning. And so, one might ask, what if you were to accidentally drink methanol? What would you want to do? Because the problem, of course, is not the methanol. The problem is the enzyme in your liver, which is chemically transmuting this methanol into something more toxic. Well, actually, the antidote for methanol poisoning is more drinking. So you actually can add more ethanol to your body in the form of drinking, or in fact, hospitals sometimes have IVs of Everclear, and they will actually add ethanol to you, and the ethanol will compete. It'll compete for the enzyme. So the enzyme now only has ethanol to work with, and then the methanol will just kind of gradually get flushed out of your body. Okay, another functional group is an amine. An amine is a nitrogen found in a small molecule, and you can kind of see it right here, right? So here there's those nitrogens found in a whole network of carbon. And don't be confused by the fact that we're not listing the individual carbons. This is a shorthand notation that's commonly seen in organic chemistry. Every time there's a vertices, that's a carbon and a hydrogen typically. So the fact that they're not drawn in there is just because the molecules are now getting so complicated that it would just take a long time to kind of draw it all out. Okay, so an example of an amine, many biologically active drugs and pharmaceuticals have nitrogens in them. Often amines are quite biologically active. And so a great example of this might be heroin. So morphine is this molecule right here. And if you want to convert morphine into heroin, they're very similar molecules. You can see here, all you're going to do is simply modify the alcohol groups on the end into these things called esters, which is another functional group. And then heroin is quite good at getting into your body and then actually passing what's called the blood-brain barrier. So there's a barrier that exists around the membranes of your blood vessels in your brain to prevent molecules from freely moving into your brain, which has to be a kind of a protected compartment. Morphine is not great at passing through this. How heroin, after it's been chemically modified, is really fantastic. So the heroin passes through the blood-brain barrier quite easily, and then actually, interestingly enough, the enzymes in the brain actually remove these chemical groups and reform morphine once it's into the brain. So in fact, heroin is really just a morphine delivery reagent or delivering system of getting morphine into your brain, where then it can act on the opioid receptors in your brain. Okay, so another common functional group might be a carboxylic acid, and here we have a carboxylic acid, and this is butanoic acid, and so butanoic acid smells just really terrible. It's the smell of rancid butter, and a lot of acids smell bad, and so a lot of times when microbes undergo kind of chemical reactions on food, that is to say that they spoil food, they will actually produce carboxylic acids, and so we've evolved as a species to kind of pick up and smell that spoiled food, and we smell these molecules as bad. And so butanoic acid, as I said, is like a rancid butter smell. And the Greenpeace boat right here, which sometimes will go up to Japanese whaling vessels and protest of their whaling efforts, and they will actually take bottles of butanoic acid, which smell terrible, and they will throw it onto the deck of the boats, and in hopes of both grossing out the Japanese whalers, as well as maybe even spoiling some of the meat, to making it really just a horrible smelling compound or smelling meat, so that you can't eat it. Okay, so in a lot of covalently bound molecules, we are concerned with really kind of two things. We're concerned with the shape of the molecule, and that we get from chemical bonding of all the different groups. And so we can kind of see here that in Tylenol, this is a 6-membered ring. It looks pretty flat, and then we kind of have like this kind of maybe this trigonal planar structure there, and so on and so forth. Whereas we can see in the heroin molecule, we have kind of these bending and curving groups, and it's kind of a cool three-dimensional kind of a structure. So we're interested in the shape. The shape certainly has a lot to do with what it does, but we're also interested in the functional groups, and that also is gonna really kind of guide and determine what it does as well. And so it's important for us to appreciate that if you have things like carboxylic acids, it's going to do something fundamentally perhaps differently than maybe these esters would in heroin, and so the different combinations of functional groups as well as the differences in its shape is going to give the molecule, it's going to kind of define what it does.